The next unit we're going to be dealing with is going to be on series and sequences and sets of numbers. So let's start today with discussing what a sequence is. A sequence is an ordered set of numbers. So if you look at the set I have here, I have the numbers 2, 5, 8, and 11. And guys, it should be pretty obvious that this is a sequence that is increasing by 3 to get from one term to the next. Well, when I have a sequence, I am going to be looking at the terms and trying to eventually determine a formula to find a specific term. So when I define the terms or describe them, I will use what we call subscripts, the little numbers below or a variable. So we would call this a sub 1, and that's the first term, and it's 2. We would say that a sub 2 would be 5, a sub 3 would be 8, and so on. And each number or each member of our sequence is a term, and we use subscriptive variables to describe those. If we have a set number of terms, then we say that that is a finite sequence. If the sequence goes on without bound, then we would say that it's an infinite sequence, which means there's going to be an infinite number of terms. We're going to spend most of today just working on how to write out terms of a sequence. So a lot of times we'll define a sequence using a formula similar to this. So we might have a sub n is equal to 3n minus 2. Then they're going to tell you what they want n to start with. So they might say something like they want you to start with n equals 1. Sometimes they'll say n equals 1 or n equals 0. Those are the two most common numbers that you start with when you start a sequence. I'm going to go ahead and write these out with detail the first time, but you'll start to see that there's patterns and you can write them pretty quickly. So a sub 1 would be 3 times 1 minus 2. Well, that would just be 1. A sub 2 would be 3 times 2 minus 2, which would be 4. A sub 3 would be 3 times 3 minus 2, which would be 7. And a sub 4 would be 3 times 4 minus 2, which would be 10. So our first 4 terms would be 1, 4, 7, 10. And again, if you look at your sequence, guys, it's pretty obvious to tell that's what's happening here is that we are increasing by a factor of 3. That goes up by 3. So once I start to see that pattern, I could go ahead and tell you without working into the formula that if I go up 3 more, my next term would be 13. Now let's use the formula a sub n is 3 plus negative 1 to the n. So a sub 1 would be 3 plus negative 1 to the 1, which would be 3 plus negative 1, that would be 2. A sub 2 would be 3 plus negative 1 squared, which would be 3 plus 1, that would be 4. A sub 3 would be 3 plus negative 1 cubed, which would be 2 again. And a sub 4 would be 3 plus negative 1 to the 4th, which would be 4 again. Notice that in this sequence, our numbers are just alternating between 2 and 4 every time. So I could again follow this pattern and tell you what a sub 5 would be and a sub 6 without actually having to work those out. Let's consider this formula. A sub n is negative 1 to the n over 2n minus 1. So again, a sub 1, we're going to let n equal 1, would be negative 1 to the 1 over 2 times 1 minus 1. Well, negative 1 to the 1 is negative 1, and then 2 times 1 minus 1 would be 1. So that's negative 1. A sub 2 would be negative 1 squared over 2 times 2 minus 1, but that's 1 over 3. And you're going to want to leave anything that turns out fractional, you'll want to leave it as a fraction. You can simplify them, but as we're looking for formulas, probably starting tomorrow, a lot of times you don't even want to simplify your fractions. For today, if fractions simplify, go ahead and simplify them. So a sub 3 would be negative 1 to the third over 2 times 3 minus 1. But that would be negative 1 over 5. And a sub 4 would be negative 1 to the fourth over 2 times 4 minus 1, which would be positive 1 over 7. Now again, I'm showing you quite a bit of detail on working these out. I understand that you could probably substitute in and be able to just write down the answers for several of these, so you don't have to show as much detail on all of these problems. I'm just doing it because this is our first time talking about these. You can also use this idea of sequences to find a specific term in a sequence. So let's say we have the sequence 2n over n squared plus 3, and I want you to find the 13th term. So all I have to do is just put 13 in for n. Well, if I do that, 2 times 13 is 26, and if I do 13 squared plus 3, I get 172. So like I said, for today, I want you to simplify these if you can, and that does simplify to 13 over 86. Now we're going to look at an alternate way that we can define a sequence, and that is to define them recursively. A function that is, or a sequence that is defined recursively, each term depends on a previous set of terms. So sometimes it may only depend on one previous term, or sometimes it could depend on more than one. There's a really famous recursive sequence called a Fibonacci sequence, which is named after an Italian mathematician named Leonardo di Fibonacci. The sequence goes like this. The first two terms are given to you. They're the numbers 1 and 1. Then to get every term in the rest of this sequence, you add the two previous terms. So 1 plus 1 is 2. Now to get the next term, I'm going to add 2 plus 1, and that's 3. Then I'm going to add 2 plus 3, and that's 5. 3 plus 5, that's 8. 5 plus 8, that's 13, and so on. Now the recursive formula for this looks like this. You got to define the first two terms, and Fibonacci actually defined the first one instead of a sub 1 as a sub 0. So he said a sub 0 was 1, a sub 1 was 1, and then to get the next term, which we write it as a sub n, is a sub n minus 2 plus a sub n minus 1, where n is greater than or equal to 2. So if I think about this, if a sub n is my current term, then that means that I want to add two terms before that. N minus 2 would be two terms before that, plus n minus 1, a sub n minus 1, is one term before that. So I want to do the second previous term plus the previous term, and then that added together gives me the current term. So if I look at that numerically, let's just write these down. A sub 0 was 1. A sub 1 was 1. A sub 2, substituting into the Fibonacci sequence here, a sub 2 would be a sub 2 minus 2, that's 0, plus a sub 2 minus 1, which is 1. So add a sub 0, which was 1, plus a sub 1, which was 1, and that gets me 2. And I could continue that same idea to find a sub 3. To get a sub 3, I would add a sub 2 plus a sub 1. Let's take a moment now and work through a recursive formula. So let's say we have a sub n plus 1 is 2 a sub n minus 1, where n is greater than or equal to 1. So let's go ahead and put 1 in first. So that would give me a sub 1 plus 1, that'd be a sub 2, is 2 a sub 1, I'll go ahead and put the number in this time, minus 1. But that's 2, and we need to know a sub 1 is defined as 2. a sub 1, and they have to give you this initial term or initial terms, depending on how many you're using to find your next value. So 2 times 2 would be 4, 4 minus 1 would be 3. So how would I get a sub 3? Well, I would let n be 2. So a sub 3 would be 2, a sub 2 minus 1, which would be 2 times, well, we just calculated a sub 2, it was 3. So then that would be 6 minus 1, which is 5. If I let n be 3, then I'm going to get a sub 4, because it would be 3 plus 1, would be 2 a sub 3 minus 1. Well, that's 2 times a sub 3 we just calculated was 5 minus 1. So that would be 10 minus 1 would be 9. Now we should be able to see that to get a sub 5, I need to take 2 times a sub 4, which was 9, minus 1, which would be 17. And I can continue that pattern to find as many terms as I need. The last thing I want to look at with you today with writing out sequences is something called a factorial. And you should have talked about these in Algebra 2. And remember that a factorial is defined as, in factorial, is 1 times 2 times 3 times 4 times all the way out to n. With the special case that 0 factorial is defined to be 1. So if 0 factorial is 1, then we know 1 factorial is also 1. 2 factorial is going to be 1 times 2, which would be 2. 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, 24. And then 5 factorial is 120. Let's write the first 4 terms of the sequence defined by a sub n is 2 to the n over n factorial. A sub 1 would be 2 to the 1 over 1 factorial. Well, that would be 2 over 1. It's 2. A sub 2 would be 2 to the 2 over 2 factorial, which would be 4 over 2, which would be 2. A sub 3 would be 2 to the 3rd over 3 factorial, which would be 8 over 6, which we know simplifies down to 4/3. And a sub 4 would be 2 to the 4th over 4 factorial, which is 16 over 24, but 16 over 24 is going to simplify to 2/3. Let's wrap up today's discussion with using this concept and idea of factorials to simplify factorials fairly quickly without having to actually do all the multiplying. So let's say I want to simplify 8 factorial over 2 factorial times 6 factorial. So I know that 8 factorial is just a product I know that 8 factorial is just the product of all the integers out to 8. And then the same thing with 2 factorial and 6 factorial. But once I expand all of that, look what happens. I have a whole string of numbers 1 through 6 on the denominator and a whole string of numbers 1 through 6 on the numerator that I can simplify. So now I'm just left with 7 times 8 over 1 times 2, which I could also simplify. 2 would go into 8 4 times and get 7 times 4 is 28 over 1, but that's just 28. And notice I did not have to multiply those factorials out because I could simplify and cancel a bunch of the terms all at once. All right, let's try another one like that. So if I expand these, I end up getting, now once all of that is expanded, I can start looking at canceling some things out. So I have a 1 times 2 here and a 1 times 2 here. And then I have 1 through 5 on the top and 1 through 5 on the bottom. So that leaves me with just 6 over 3, which is 2. Now, I know that probably some of you can look at this and see that if I have 1 times 2 here and 1 times 2 times 3 in the denominator, that's going to leave me a 3 in the denominator. And the same thing with this set of terms. You've got a 6 factorial and a 5 factorial. Well, the 5 factorial will cancel out with the first 5 terms in the 6 factorial. So that would leave me with just 6. And 6 over 3 would be 2. All right, now let's wrap up with a couple that are a little more abstract because we really aren't going to have numbers like we had before. We had 6 factorial. Now we've got n factorial. So guys, again, applying this idea of factorials, n factorial we know is 1 times 2 times 3 all the way out to n. And n minus 1 factorial is 1 times 2 times 3 all the way out to n minus 1. But then if we think about in the numerator, if the last term is n, the number right before that has to be n minus 1. So if this is 7, then the one before it is 6. One number shorter than that, or less than that. So if I can think of it that way, now I can see there's going to be some stuff that cancels. Here's 1, 2, 3 all the way out to n minus 1. And in the numerator, I've also got 1, 2, 3 all the way out to n minus 1, which leaves me with just n in the top. So n factorial over n minus 1 factorial will simplify down to just n. Let's wrap up with one more example. So we have n plus 1 factorial over n minus 1 factorial. So expanding, we get, notice that n plus 1 has more terms than n minus 1 factorial. So we're going to go back to the n plus 1 and write a few terms that were before n plus 1. Well, right before n plus 1 had to be n. And right before n had to be n minus 1. Now we should be able to cancel. So if I look on the bottom, I've got 1, 2, 3 all the way out to n minus 1. And on the top, I have 1, 2, 3 all the way out to n minus 1. All that's left then is n times n plus 1. And you'll want to leave your answer in that form. Do not worry about distributing through. We want to leave our final answer as n times n plus 1.